Oh, hello, and welcome back to Math and Tea, the show where we talk math and drink tea. I'm your host, Dr. Joseph Van High, and in today's episode, I want to talk about one of the coolest things in all of mathematics, and unfortunately, most people never get to see it. It gets barricaded behind a class that people just don't take unless they're going to become a math major, and, well, let's be frank, most people don't become math majors. And this fact is about a surprising thing: counting. And, we don't think too much about counting. It's just something we do. And if we turn counting into a rigorous, logical, mathematical thing, then something surprising happens. So let's practice counting. How many fingers am I holding up? Well, 3, right? But how do we know that? Because we count them like so. 1, 2, 3. And what we're doing here is we're pairing together numbers and objects. 1 goes to this, 2 goes to that, and 3 goes to that. Order, you'll notice, doesn't particularly matter. I can just as easily count 1, 2, 3, or 1, 2, 3, or 1, 2, 3, or a number of different ways. But you'll notice there's also some special rules on how we count. For starters, we're not allowed to do anything twice. We're not allowed to double up. So for instance, I can't do 1, 2, 3, 4 and say there's 4 objects here. I also can't do 1, 2, 2 and say there's only 2 objects here. In the same way, I'm not allowed to skip over things. So I can't say 1, 2 and say there's only 2 objects. And in the same way, I can't say 1, 2, 4 and claim there's 4 objects. Everything has to be paired up, but only one time. Now here's something else to note. When I count, I don't count with a single number. I have to count with a bunch of numbers, everything between 1 and, well, in this case, 3. So I'm not counting with a number in a pure sense, I'm counting with a set of numbers. And I also started with a set of objects, my fingers. So counting is really about comparing two sets. In this case, the set of numbers, 1, 2, 3, and the set of my fingers, this finger, and that other finger too. Now let's go to some slides and talk a bit more abstractly. Here we have two sets, one on the left, one on the right. We see that these two sets have the same size. Well, technically we say they have the same cardinality. If we can pair up the elements in each set with nothing being repeated and nothing missing. Also, we're not allowed to pair up two elements in the same set, they have to cross between one set and the other. These two sets have the same size, because I can pair up their elements like so. Nothing has been repeated and nothing has been skipped over. In fact, we can do this a bunch of different ways, just as I did with my fingers earlier. And there are some ways that don't work. All that matters, though, is that we're able to do it at least once. If we do it once, we're good. They have to have the same size. This also gives us a way of showing that two sets aren't the same size. If, for example, no matter how hard we try, no matter which combinations we attempt, we either double something up or we miss something. But if two sets aren't the same size, one should be larger than the other. How do we tell which in a purely mathematical way? Well, if we try and build up such a pairing between the sets, avoiding all repeats, and in one set we're always left with something left over, something that was missing, then that set has to be the bigger one. By the way, if you're interested in the technical mathnobabble that's going on behind this, we have an injection that's not a surjection. Okay? Back to the slides. This is how we count in the abstract, and how we're able to tell whether or not a set of objects has a larger, smaller, or the same number of objects in it as another set. And here's the kicker to all of this. The sets we are trying to count don't have to be finite. All we care about is pairing things up properly, and we can do that whether or not a set is finite or infinite. Now, if we think infinity, we're typically thinking of counting to infinity, going 1, 2, 3, 4, and so on forever. So our prototype infinite set will be the so-called counting numbers, the positive integers, like so. This allows us to compare various infinite sets, and, if we want to extend the analogy, to see what happens to infinity when we manipulate it by adding, subtracting, multiplying, and so on. First, let's consider what happens when we add 1 to infinity, or, that is, add one element to an infinite set. In this case, we can choose to add the number 0 to the set on the right, but this quick rearrangement shows that these two sets are still the same size. Infinity plus 1 is still infinity. What if we take all of the integers, positive, 0, and negative? Well, as you can see, these can still be arranged to pair up nicely with the positive integers. everything will eventually get paired up exactly one time on both sides, even if it does take a little bit longer to get to larger values on the right-hand side. So these two sets are still the same, and since negative plus positive tends to double things up, we can think of this as infinity times 2 is still infinity. We can even move to much bigger sets, like the set of all positive rationals. It's a little harder to show it, but it turns out it's still the same size as the set of positive integers. It's still infinite. Now, note we have to be a little bit careful and skip things like 2 over 2 in our example, since that would be a repeat of 1 over 1, and we can't do repeats. And we could argue that the size of the rationals, since it's basically any integer we like divided by almost every other integer we like, is something like infinity squared. So infinity squared is still infinity. Now at this point you might think this is an exercise in futility. All I've shown thus far is a bunch of infinite sets that have the same size. This is not so surprising. If something is infinite, then it's infinite. Infinity is infinity is infinity. And there's only one infinity, right? Okay, let's move up one further level of complexity to the set of all real numbers, the set of numbers that can be written down with a decimal expansion. This includes numbers like 1, 2, 3, and 5/6, but it also includes things like pi and the square root of 2, which aren't rational numbers. But for simplicity's sake, let's restrict ourselves to a small part of this set, the set of numbers between 0 and 1, including 0, but not including 1. These are the numbers that can be written as 0 point blah blah blah. Here I've illustrated one potential way that we might try to pair up these two sets, our original set of all the positive integers and our set of numbers between 0 and 1. It's clear we matched up everything on the left-hand side, but what about the right? Did we get everything? Consider the numbers highlighted in red, and let's create a new number, a new real number, that is formed by taking each of these integers and adding 1 to them, and if we're at 9, zooming back around to 0. Like so. The new number here is not in any of the pairs. It's clear to see that it disagrees in the first position with the first number, because, well, it's 1 off. It also disagrees with the second number in the second position, and with the third number in the third position, and so on. In fact, it's going to miss every single number on the list because it's always going to disagree with each such number in at least one place. So clearly, this particular pairing isn't going to work. We've missed this number at the bottom. But as it turns out, there was nothing special about this initial choice of pairing. If I put a different suite of numbers in, I can still look along this diagonal, add 1 to each digit, and see the same problem arise. So no matter how I try and pair things up, I'm always missing something from the right-hand side. Okay, I'm eliding over one detail here. Real numbers can have multiple representations. It's not that hard to get around, but it's technical, so I'll avoid it. So despite the set of positive integers and the set of reals both being infinite sets, one is clearly of an order larger than the other. All infinities are, as it turns out, not created equal. We call infinite sets that have the same size as the set of positive integers countable, for kind of the obvious reasons. We're counting them. Sets that are larger than that are uncountable. And there's no reason this process has to stop here. You can find sets that are even larger than the set of reals. There aren't just 2 infinities, there are infinitely many infinities. And they are vastly, vastly larger than the infinity plus 1 you may have joked about as a kid. Wild, huh? Now, as you can imagine, this talk of infinitely many different infinities caused a bit of a stir when it was discovered back in the day by Cantor, a German mathematician. Now, some of Cantor's contemporaries thought he had, well, lost his mind, and the rejection of his colleagues likely caused depression in much of his later life. But these days, we see Cantor as a visionary, and his work on infinity has been described as a paradise of mathematics. But that's all for now, because I'm out of tea again. Bye.